My name is Jia. I work at Oracle. I'm super excited today to take you on a cool journey. We're going to go under the hood of an Exadata transaction, and we're going to see how we harness the power of persistent memory to help us greatly boost our OLTP application performance. As we get started on the journey, I'd like you to meet an Exadata X8M rack. You can see it on the slide. You can also see it on my backdrop. Exadata is the best platform for an Oracle database customer to run their database workloads. We support both the OLTP workloads as well as the data warehousing workloads on Exadata. We give them the best performance, the best scalability, and the highest availability on the platform. So to break down the Exadata system, let's take a look at the hardware components first. So inside a rack, we have two types of servers. We have the database servers. This is where we run our database software. And then we have both a 2-socket server shape and a 8-socket server shape, depending upon the customer's needs. And this is where the database software runs, and we use the latest and greatest CPU chips from Intel to make sure that they run at their fastest. And on the other hand, we have storage servers in the rack as well. Storage servers is where the data actually resides. So a very popular option is what we call a high capacity server, where we have 168 terabytes of hard disk storage in each server. And on top of that, we're adding a 25.6 terabytes of PCIe flash. This allows us to actually build a flash cache tier on top of the hard disk to greatly accelerate the IO performance. The other option for the storage server is a all-flash storage server. We call it Extreme Flash, and it has about 51.2 terabytes of flash in each of the servers. Now you know we have the two different kinds of servers. You'll be asking me, Jia, how do the servers talk to each other, right? What networking technology do you guys use? So as you can see on the slide, we use 100 gigabits RoCE. RoCE stands for RDMA over Converged Ethernet. So in the earlier days of Exadata, we've been running RDMA over InfiniBand, and Ethernet has totally caught up in recent years. So we've cut over to use Ethernet as well. But RDMA has always been very important to us because it gives us the lowest network latency, the highest network throughput with the lowest CPU overhead on the hosts. And we're going to talk about RDMA a bit more down the road. Last but not the least, I'd like you to meet this persistent memory module. So this is the actual PMEM, the picture of a PMEM that we use in our storage servers. And we managed to pack 1.5 terabytes of persistent memory in each of our storage server. And by combining persistent memory and RDMA, they produce amazing chemistry that really helps us greatly improve our OLTP performance. And I'm going to share the details with you shortly. All right, so this is a quick word on the elastic expansion capabilities of Exadata. So don't think of Exadata just as a single rack that you saw, that you see on the backdrop. We can start, incrementally very small, adding more servers as a compute or storage needs were to arise, and they can get built into multiple racks. So it's really a good scaling story as well. And this slide I really like this slide because it summarizes the core values of Exadata. We provide the best, the ideal database hardware to run a database workloads. We build database-aware smart storage software to greatly improve OLTP data analytics and consolidation workloads. And we also provide an automated management stack that really makes our customer have the best experience using Exadata. It's on-prem, it's in the public cloud, it's also available through a cloud at customers. So there's very many different ways for a customer to deploy their Oracle database workloads on Exadata. And this slide shows, a sample of our, very important customers. And as you see, we've been around for over a decade, since 2008, and 87% of Fortune Global 100 run on Exadata. So this really shows how popular Exadata is, and then the most critical customers are running their most mission critical workloads on Exadata. That includes both data warehousing and OLTP and consolidation. And for this presentation, I'm going to really focus on the OLTP capabilities of Exadata. All right, so now let's go under the hood of an Exadata transaction. So OLTP, I believe everybody who comes to Sigma would know it stands for Online Transactional Processing. So in this case, let's meet Ben. Ben is an OLTP application user, okay? He wants to deposit $1,000 to his bank account. So how does that work? How does that translate into database actions? So first, the application is going to send an update SQL to the database, let's say to an Oracle database in this case. And an Oracle database is going to parse this SQL, and to parse it, like all the information about the schema, about the table, is all usually readily available in the main memory of the database server, right, where the database software runs. So in the library cache, as we call it. And then we create a cursor, which is basically a encapsulation of what we're going to do with this SQL. And all that operation is strictly in memory, super fast. Then, as part of executing this cursor, the database is going to traverse a B-tree index, because this is a typical way of quickly looking up a record. In this case, we're probably, traversing the B-tree using a primary key lookup, let's say using Ben's user ID or account ID. And again, because index blocks is very frequently accessed, they're readily available in the buffer cache of the Oracle database. So we don't have to go to disk, we don't have to go to storage. We run at CPU and memory speed, which is super fast. The next step, we found Ben's block, okay? So we know where his accounts reside, but we're having trouble finding that block in our buffer cache. What happened in that case? So as it turns out, the data is actually not in our main memory, so we call it a miss. When you have a miss in the buffer cache, what do? Right, you perform an I/O. You go to the storage, because that's where all the data resides, and fetch the block that you need. And in this case, I kind of dramatize the effect a little bit here, but I call the fact that by going to the storage, we actually essentially falls off an I/O cliff. The reason I say I categorize this as an I/O cliff is because prior to this step, the 3 steps as you see on this slide, they're all running, on the CPU, out of memory, or perhaps even CPU cache, so at very fast speed without any stalls. But as soon as you go to the storage, you know that you're gonna take a hit that's an order of magnitude longer than you were previously experiencing, so the application really runs into a grinding halt. So here comes our OLTP challenge number 1. What is the I/O cliff for this random data read? So in this case, as you may remember, Ben's record sits on a block that's not in my buffer cache. So what do I do in that case? The database figures, okay, I got to go to storage and read that block back. So when the database goes to the storage and starts reading that block back, it simply sends a message to the storage server first, right? And tells the storage server where to read the block. And the storage server, as I mentioned in this case, let's say this is a high capacity server. So the data normally sits on the hard disks, but hard disk, as we know, is very slow. You have to go, take the hit of a seek latency, rotation latency before the data starts to transfer. So it's like, milliseconds or tens or hundreds of milliseconds later before you get the data. So that's way too slow, not good for an OLTP application. So let's say Ben get lucky. His data was actually cached in a flash cache, front-ending that hard disk. So the storage server is able to actually read that block back from flash and sends it back to the database. And then the database puts it into its buffer cache and it's ready to continue with its processing. So the question is, how long do you think this random block read actually takes? In this case, we actually read it from flash. So let's break it down. I think it's very interesting to dissect an I/O and then see where the time is spent. So as you have learned by now, when the database performs an I/O, it actually does a bunch of work underneath the cover, right? the database application has to go through a kernel user context switch in order to send a message out. And on the other end, on the storage server side, the kernel will pick up this message and gets an interrupt and have to wake up a storage server process and ask the storage server process to continue to processing. And then the storage server process will then issue a local read from its own flash, right? And be able to return the block back. In this case, I'll tell you that the latest and greatest flash technology today will probably give you like a sub 100 microsecond AK local read latency. So now you wonder, okay, I know it takes about 100 microseconds to read from the flash. And then how long does end-to-end does this block read take? And I'll give you another clue. All the software overhead on the networking stack, for example, on sending the messaging, processing the messaging, and context switches and whatnot, they also add up to about 100 microseconds. So if we do the math, it's pretty straightforward. 100 plus 100 is 200 microseconds. Now we know, okay, so if we were to go to the storage server, perform a read on the flash and get a block back, it takes us about 200 microseconds. And some of you might say, Jia, don't call it IO cliff. 200 microseconds is very fast. I agree with you. I'm actually picking on our own technology. I'm picking on this 200 microsecond latency that's actually measured and observed on the Exadata rack prior to the advent of persistent memory. So it is actually already really fast as you look across the industry. But can we do better? With persistent memory, how do we conquer this random read IO cliff? So I like to show you this dynamic dual, this jigsaw puzzle. We have persistent memory on the left hand, and we have this networking RDMA technology on the right hand. So how does this dynamic dual help us get over this IO cliff? First, let's take a look at persistent memory. Persistent memory is a new silicon technology. Intel first unveiled this technology in 2019, and that's when Exadata X8M shipped out with the persistent memory support. And persistent memory, if you look at the technology of various media, there's DRAM, there's flash, there's hard disk. It's really in between DRAM and flash. It's about 2 to 3x slower in terms of a read access compared to a DRAM, but much, much faster than a flash. And then it has a very nice capacity pricing and performance point in between DRAM and flash. And the ability to be able to sit on the CPU socket through the persistent memory module gives us abilities that, create really creative opportunities for us. I'm going to show you, very, very, very soon. But let's finish the discussion on persistent memory here. The really important thing about persistent memory is that it's actually the writes, the stores to the memory can survive power failures, unlike DRAM. So that's really new and groundbreaking. But the problem with utilizing that capability is it's actually not trivial. It requires quite sophisticated algorithms to maintain the integrity of data on PMEM in order to survive a power fail. I'm going to talk a bit more about those 2 points a little bit later. But first, to keep in mind is that the CPU cache, all the stores in the CPU cache are not persistent. So you got to make sure your stores go to PMEM. Bypassing CPU cache will get flushed from it. Secondly, PMEM write atomicity is at a different level from the traditional media write atomicity, like a sector level. It's very different, and that poses unique challenges to a database application as well. Okay, let's look at the second player, remote direct memory access. The acronym is RDMA. So RDMA is a networking technology where it allows one end, like one process, for example, in this case, a process running on the database server, it can first map its memory region to this RDMA-enabled NIC card. And similarly, on the storage server side, it can do the same. So both sides, I have some memory region that's pre-mapped to my RDMA-capable card. And then what happens is between those two cards, they can create a connection and they can exchange keys so that they set up the ability to perform a remote direct memory access. And then later point in time, let's say the database server wanted to go direct to probe into the storage server's memory, it can just do that directly without even having the storage server be aware of it. So it's completely self-serviceable from a database server point of view. And he can do an RDMA read of the remote memory. He can do an RDMA write of the remote memory. So both directions are possible. And then we actually exploit both capabilities to boost our OLTP application performance. Okay, so let's come back to this IO cliff picture. So how do they, RDMA plus persistent memory, help us conquer the IO cliff? So the first thing one might be thinking of is, look, well, you tell me, flash is super fast, right? It's close to memory speed. So why don't I do a drop-in solution? Let me put persistent memory on top of my flash cache, right? Because flash has 25 terabytes, persistent memory, I only have 1.5 terabytes, so it's much smaller. So let me build a tiered cache, right? I put PMEM cache on top of my flash cache, and then I let that serve the OLTP random block reads. Would that help? Sure, that's a great idea. Let's try it out. So as you know, all that messaging protocol doesn't change, right? So we're still spending 100 microseconds on the messaging part. But what is different in this picture is the latency for flash read goes away, right? Because we're not reading flash anymore. Instead, we're just getting that AK block direct from a persistent memory cache. And our performance data shows that it takes about anywhere from 1 to 2 microseconds to perform a 8K data block read from a persistent memory. And that number varies depending on whether you're accessing a socket local memory or you have to go across a UPI link to access a remote memory sitting on the other CPU socket. But in any case, it's 1 to 2 microseconds. So that's really a drop in the bucket compared to, 100 microseconds, right? So then what is the IO cliff now? What is the end-to-end latency? Oh, great. We've drastically cut the latency to 100 microseconds. Let's celebrate. That's a great accomplishment. But somehow you would feel that, look, my PMEM reads only take about 1 to 2 microseconds, but the database still has to wait for 100 microseconds to get its block back. It's kind of not completely satisfying, right? So it begs the question, can we do better? And our answer is yes, yes, we can. And we actually implemented a radical approach in our mind is that, look, this whole 100 microseconds that's involved in the messaging protocol is what we really don't like, right? That adds all the fat to the IO path. So can we actually take that out completely, get rid of them, and replace it with this RDMA technology that we just talked about? Can the database server perform a direct remote memory access to the persistent memory cache on the storage server and be able to get that block back quickly, much, much more quickly? So in that case, what happens to the IO cliff? Oh, well, I can give you a sneak preview. In our test, we're able to actually accomplish sub 19 microseconds. And this is, if you remember the 200 microseconds number, this is 10x faster, I repeat. And I also wanted to say that this 19 microsecond number is reported when you have several million IOPS happening in the Exadata rack. If you're looking at some lower IOPS, that's, the volume vendors tend to provide like, 16K, 30K, even 200K or 300K. I see a much lower latency. I've seen 13, 14, 16, So this is really a great performance boost for a random block read. So you say, okay, Jia, I really like the performance numbers. Now show me how you actually did it, okay? So here is the secret. What happens in this case is that the database first will probe a remote RDMA hash table sitting on the storage server, and to figure out exactly where my data resides, right? Because it's a PMEM cache. So it's the data sitting on the persistent memory, but from a database point of view, I have no clue where that data is. So the first step is to locate the data. Once we locate the data, let's say this is a hit, I'm able to figure out, okay, it's actually a hit in the PMEM cache. I know where to go. I just go direct to that PMEM cache location and then perform an RDMA read. And that 8K block gets returned directly by the NIC card, because the NIC has direct access to the memory that's already pre-mapped onto the NIC and return that 8K block back to the database and directly into the buffer cache. So it's 0 copy end-to-end. And this is what gives us that amazing 19 microsecond performance. And I'm really happy with this super fast IO, right? Shall we say? It's no longer a IO cliff anymore. What do I get? I get a sub 19 microsecond IO read, I guess. It's no longer IO cliff. I call this an IO trampoline. You kind of jump on the trampoline and then, you get to the other end. So this is truly transformational. It really changes an IO bound application into a like sort of a near memory application, right? It's like the kind of 19 microsecond latency is getting much, much closer to the memory performance than, the traditional sense of a networking IO. And in this particular case, what we discover is that the way to wait for the RDMA completion is actually not that tricky, because if you just sit on the CPU and pull for the completion, it's actually more beneficial for an Oracle database application process, because we tend to have a pretty large CPU cache presence. So if we were to go off the CPU, gets waken up by interrupt processing, and then bring back all that CPU context, it turns out that it performs slower, our IO takes longer, and we actually uses more CPU to do that. So that's why our implementation uses a synchronous pull for the RDMA completion, and that gives us 10x lower latency and much less CPU usage than going through numerous context switches. And well, the database gets that 8K block in memory back in the buffer cache, and then it can proceed to update Ben's transaction. All right, so is that it? Are we done with the OLTP transaction? Well, not really, right? So for all the database students, we have learned this ACID property, and D stands for durability. So in order for the transaction to be made durable, we have to not only write the redo for the changes to disk or to durable media, we also have to write a commit of the transaction to durable media. And sometimes the database can optimize those two log writes into one, piggyback both of them together. So what happens again, if you issue a log write to storage, I say it's falling off another IO cliff, right? Because you have to make a trip to the storage, and the latency involved for the log writes is order of magnitude higher than when you compared to when you're running on the CPU or the main memory or through the RDMA for your random block read. So here comes our OLTP challenge number 2. Can lightning strike the same place twice? The answer is yes in this case. So let's take a closer look at challenge number 2, redo log writes. So how does redo log make sure that it's the commits are durable? So typically the database server actually will send a message, with all the redo log information to the storage, and then the storage simply writes it to persistent media. On the Exadata case, prior to PMEM, we already have a very innovative idea in terms of log writes, is that we actually have 2 kinds of persistent media on a storage server. One is a flash log, the other is hard disk. But in front of the hard disk, we have a disk controller that actually has a battery-backed DRAM cache that we use to land writes really quickly. But both are devices that just run a bunch of code underneath. You think they're hardware, but it's like software runs everything. So they all have a bunch of software in there to manage the cache, and the flash case, the software code that does the PE cycle management, because flash you can never write in place, right? You always write a new page, and then before you can write it, you have to erase it. So all those software, whenever they run, inevitably, they're gonna have some bugs. So we have seen cases where temporarily one of those devices can go into a glitchy state. And when that's the case, the IO can take much longer. We call it IO outlier. To eliminate those outliers, what we do is we actually send writes simultaneously to both flash and the disk controller. And in those cases, whichever write finishes first, then we'll be able to add it to the database. So that's our trick prior to persistent memory to ensure super fast log writes. However, even with that trick, as you can see, how long is the log write gonna take? Right, it's still the same messaging protocol. It's still a write to either to the flash or disk controller DRAM cache. It's still around, unfortunately, around 200 microseconds. So can PMEM and RDMA come to the rescue again? The answer is yes here. So what happens in this case is that we wanted to replicate the success we had with random data read using RDMA and PMEM to accelerate log writes. So how do we do that? In this case, what we do is we actually issue a RDMA write to the PMEM log buffer that's tethered to the NIC on the storage server. So you can imagine that we carve out a bunch of persistent memory buffers and we pre-map them. We map them onto the RDMA NIC. And then when the RDMA write lands, it lands in one of those buffers. And as soon as that write lands in the PMEM, it's persistent, right? Because persistent memory is by definition persistent. So the NIC can simply send the ACK back to the database and database thinks, okay, my transaction is committed. So that gives us super low latency. And in the background, the storage server software actually gets notified whenever those redo lands in the PMEM log buffer. Then the storage server will wake up and destages the redo back to the backing stores, be it flash or hard disk. And that frees up the PMEM log buffer so we can post it back to the card for more redos. So in fact, when we implement this PMEM log, we only use less than 0.1% of our PMEM log space so that we can have a cake and eat it too, have a large PMEM cache to accommodate as much working set possible for our hot data and carve out a very small amount of space to accelerate the log writes. Okay, so a very natural question will come in terms of persistence is, what if I have a power outage? Is my redo safe? So the answer is yes and no. Intel had this networking technology called Data Direct I/O, DDI/O, that allows a NIC card to land its transfer into the last level cache. And you may remember that the CPU cache, the data in CPU cache is non-persistent across a power fail. So how do we ensure our log writes are persistent in persistent memory? So the trick here is we actually had to turn DDI/O off in our NIC card to make sure that the redo log writes end up in PMEM directly so that it can be persisted across a power fail. So that's the trick here. And then let's come back to Ben's transaction. Remember the IO cliff for the log writes? So what happens now? Well, we have 8x faster log writes because we can play the same trick and do RDMA writes to PMEM log. So net, the takeaway is please do not fall off the IO cliff. Remember using all those RDMA tricks that you have learned today to accelerate your OLTP application. And you'll say, hey, Ben, why do Ben care? He might be doing this banking on his mobile phone. It'll take milliseconds, if not centiseconds, for that phone to find the nearest cell tower. So Jia, why are you so worried about this 200 microsecond latency? But in actuality, we have seen a lot of real critical OLTP customer applications that does fraud tracking or real-time analytics upon clicks on the screen that really can benefit this kind of super low latency performance improvements. So these are the real cases that we cater to. So let me summarize my talk. We have talked about how an OLTP transaction runs on the Exadata, how we combine persistent memory with RDMA to produce this amazing chemistry. And I really wanted to thank you for staying with me on this journey. I hope you learned the secret sauce that we have. And if you have any questions, send me an email. Thank you and enjoy the rest of SIGMOD. Thanks.